In this video, we're going to start to look at some very common toxic materials, and we're going to start with the three most common toxins, and they are carbon monoxide, cyanide, and sulfur dioxide. Now, carbon monoxide is an odorless, tasteless gas. It's colorless, it's non-irritating, and it's pretty much part of every single fire scene because carbon monoxide happens as the result of incomplete combustion. So, anytime you have anything that is not burning completely efficiently, carbon monoxide is going to be there and present. The amount that is present really just depends on how much is burning, how much oxygen is available, and what the run rate is. Now, how does carbon monoxide actually act as a toxic material? Well, it interrupts your normal act of respiration by interfering with your oxygen transport. So, if you recall from our previous video talking about asphyxiants and about heme inhibiting substances, what we're seeing here is that carbon monoxide interferes with oxygen transport. That is the hemoglobin that is in the blood, and the resulting symptoms are something called anoxia. And these include difficulty breathing, drowsiness, headaches, dizziness, chest pains, and things of that nature. Now, other than as a byproduct of incomplete combustion, we can also find carbon monoxide available in liquefied compressed gas form, non-liquefied compressed gas form, and cryogenic liquid. What we see in these kinds of forms is that in addition to being a risk of fire, carbon monoxide is relatively unstable compared to carbon dioxide and will burn if there's enough oxygen present. What we also see is that because of the compressed nature, we also are going to have an explosion hazard as well. Now, because it is a gas, inhalation toxicology is the primary risk. This is where we're going to see the majority of the issues taking place with carbon monoxide. Now, the fancy term that gets put around that is something called carboxyhemoglobin. Now, carboxyhemoglobin is just a fancy way of saying, take the word down, carb, indicating carbon, oxy, indicating oxygen. So we have a carbon monoxide activated hemoglobin complex instead of an oxygenated hemoglobin complex. And so how this works is the carbon monoxide will bind to the hemoglobin in the exact same spot that the oxygen would. The only real difference is that oxygen is designed to get off the hemoglobin and get on the hemoglobin rather easily. It's meant to be exchanged. So the oxygen molecule attaches to hemoglobin in the lungs and in the blood vessels that are attached to the lungs. It's transported throughout the entire body. It gets to where it needs to go. It hops off. Difference with carbon monoxide is carbon monoxide attaches to the hemoglobin and it doesn't let go. And so it becomes very difficult for the oxygen to attach if the carbon monoxide is already there. And since the carbon monoxide does not get off easily, it just stays on there. It starts to poison the hemoglobin, makes it impossible for the hemoglobin to pick up oxygen. And so eventually the oxygen supply in your cells runs out and there's no new oxygen coming in because the hemoglobin is attached to carbon monoxide molecules instead of oxygen molecules. Probably the most common places where we would encounter carbon monoxide poisoning are in places in our own homes. So probably most commonly is if you have a fireplace, especially a wood-burning fireplace. Carbon monoxide can come off as a result of the incomplete combustion of the wood. And if the chimney flue is not open or if it's blocked in some kind of way, instead of taking those gases up and through the chimney, they can start to be dispersed throughout the home. Another possible kind of issue is with generators. Now, here in Vincennes, we just went through a bit of a power scare where we lost power for several days, and a lot of people ended up buying generators. Now, the thing with generators is they will burn gasoline or some other kind of hydrocarbon fuel. And if you're not careful about it, if you're not careful about where you use it, it can actually start to leak carbon monoxide into the area, which is why you're supposed to keep your generator a minimum of 5 feet away from anything flammable and a minimum of 3 feet away from any walls or any other kinds of obstructions, not just because of the heat generated, but because of the carbon monoxide and other things. You want to make sure that it's properly ventilated out. So that's carbon monoxide. If we look at hydrogen cyanide is the byproduct of any kind of cyanide pill or other kind of relationship where the cyanide pill or the cyanide in the air reacts with water, and you end up getting hydrogen cyanide as a result. It is a colorless gas. It has an odor that is a lot like bitter almonds, but it is highly toxic. Its threshold value is only 10 parts per million. So 10 parts per million is not a terribly high concentration, and that is the maximum that you can encounter on a daily basis, all day, everyday basis, without any kind of ill effects. Now, like carbon monoxide, it inhibits the ability of your body to utilize oxygen effectively, but it's not by the same mechanism. So, hydrogen cyanide does not mess with hemoglobin, whereas the carbon monoxide, that's its primary mode of work. But what happens with hydrogen cyanide is, like I said before, it's a gas, and what it works with or inhibits is a particular enzyme that is associated with metabolism, something called cytochrome C oxidase. And what cytochrome C oxidase does is it helps your body to break down the oxygen and to utilize that oxygen to perform cellular functions, in particular energy functions. And so what happens is the cyanide blocks this normal mechanism to use the oxygen, and the cells end up going into anaerobic cellular metabolism, which is far more inefficient, and eventually, if it continues long enough, the cells start to really get into trouble and start to die. Now, a derivative of this, if we find our hydrogen cyanide has been dissolved in water, then what we have is something called hydrocyanic acid. Hydrocyanic acid is a colorless substance. It is extremely volatile, so it's very easily gasified. And where we see it used primarily is for large-scale fumigation operations. So if we're trying to kill bugs, vermin, rodents in large kinds of areas, and we're fumigating the whole building, fumigating a whole greenhouse, hydrocyanic acid is one way that it is done, where you're able to completely clear the area and very quickly kill pretty much any living thing that is inside of these large square footage kinds of areas. The last toxin that we're going to talk about today is sulfur dioxide. Sulfur dioxide is also colorless, also toxic, but has a really sharp odor. We can associate that with burning tires. Another way to think about it is burning hair. The main idea is that sulfur dioxide has an odor. It's quite strong, but if you were to try to describe its odor, it'd be kind of difficult to do. There are things that it kind of smells like, but with a much higher intensity than anything that you're talking about there. So, like if you burn tires, yes, there are some odors that go along with that, but unless you're standing right on the tire and you're just sniffing the sulfur as it smolders off of there, you're probably not going to get a strong sulfur dioxide smell. You're going to get a strong combustion, burning kind of smell, unless large amounts of sulfur dioxide are being produced in the process. Same with burning hair. Burning hair has an odor, but there are more things than just sulfur that are being burned in those reactions. Now, where do we encounter sulfur dioxide? Any fire that involves sulfur or sulfur-containing substances. So the reason why we can associate with tires, sulfur is used in the vulcanization process to help harden rubber. Um, why do we smell sulfur in burning hair? Most hair has sulfur that help to link the proteins together in it. We can buy sulfur dioxide as a liquefied compressed gas, and its concentration in normal air is used as a criteria air pollutant. So sulfur dioxide is also associated with a very common pollutant that you see in big cities. We call smog. That combination of smoke and fog, sulfur dioxide is usually quite prominent in that mixture overall. Now, one thing that sulfur dioxide also does is that when it is released into the air, it will very slowly convert from sulfur dioxide to sulfur trioxide. And sulfur trioxide can react with water to make sulfuric acid. And this combination of materials, water and sulfur trioxide, give us sulfuric acid, which can travel around in rain clouds and produce acid rain. Now, as far as some of our placarding and safety concerns, we can see that sulfur dioxide on its own is not flammable. It is not, reactive in the sense of being explosive. It's relatively stable. But as far as a health hazard concerns, it's a moderately high health hazard. And for those reasons, it gets this toxic skull and crossbones GHS placard with it as well. Now, because it is a gas, once again, we are seeing toxicity coming primarily from the inhalation as opposed to ingestion or absorption. We will begin to notice immediate symptoms at concentrations of 10 parts per million. So just like we saw for the hydrogen cyanide, 10 part per million is the threshold limit value for HCN. We actually start to see symptoms at 10 parts per million for sulfur dioxide. So pretty toxic stuff. And finally, as mentioned before, there are many commercial products that are sulfur derived or contain sulfur derivatives. And when these substances burn, you're going to find sulfur turning into sulfur dioxide. That is going to be the primary mode of combustion for the sulfur atoms in those substances. So that's where we'll stop our discussion for now. In our next video, we will talk about some other common other common reagents that are toxic, including hydrogen sulfide, nitrous oxides, and some others. Have a good day.